afterwards. But, yeah.
I cannot just put this on one only.
Yeah.
Right.
So I
Good
think
point. Good. Yes.
if one is
Yes.
complex, we should be able to do
Yes.
it.
Right. Good point. Anyways, back to the
meeting.
Well, I just wanted to stare at the that figure.
You're still before 12. So.
Oh, good.
Well, how long are you aiming for anyway?
How long would you like me to?
Yeah.
You tell me when I.
If you
first time
people like when we're done by 1.
Yeah.
Including all the wrap up questions, whatever late
Makes
start.
sense.
So I would say 45 minutes for the talk, and then there will be questions and. But it's not super.
All good. All good. So.
Ist das so?
So good.
Wir haben das alle auch genug gemacht. Ne?
Ja.
Es ist tatsächlich erst 12.
Ist gut. Können wir dann auf Zoom? Wait,
Ja,
Moment, ist Zoom? Wait, Moment.
Wo ist dein Zoom hin? Das weiß ich
Mein
nicht.
Zoom ist jetzt weg. Warte mal.
Ne, Talking Carola Wenk. Nee, ich glaube, dein Zoom ist, weil du.
Ach so, mein Zoom ist nur.
Du siehst ihn nicht. Ja, da ist er. Wenn er zum Talking sitzt, dann.
Kriege ich den dann wieder an?
Das ist eine gute Frage, keine Ahnung.
Sollte ich einmal ausprobieren.
Da zum Beispiel. Die Anna ist da, ja, wie schön.
Oh, hey Anna.
Hi there.
Joining. I think I can't hear you, but
you can't
I
hear
should
me?
be able to hear you. Anyway.
I don't think she can see you. I don't have a
Oh, okay. No, that's fine. All good.
But she presumably can hear you.
Yeah, very nice.
Good.
Very good. Okay, well, let me go back then. Okay, so somebody check that I'm sharing the correct thing. Right?
Yeah, Haley is keeping an eye on what's happening on the Zoom, so hopefully that's
just I'm still sharing it, yes? I'm kind of amazed.
Yep, look, there's
that the controls are just gone. Cool. Okay.
Yeah.
Okay.
Good. So I think we can get started and too late, so probably roll in. So the story of this talk is that this week is a pretty crazy week if you're in competition geometry, in that there's first the Canadian Conference on Competition Geometry, and then the week after there's the graph drawing. So it's all pretty busy right now, but the nice thing about it is that lots of people that I know get to see a lot happen to be nearby, and I'm like, why don't you come visit me? So this is what brought Carola here. The invited speaker, it's his here. And I've known Carola since I don't know when. We must have overlapped as undergrads. I looked at your CV.
Yes, we must have.
There was a year also, but I don't remember calling you, meeting you, but something there. So that Carola did her undergrad at Berlin, and then went to stayed there until the PhD with Helmut Alt at the Free University of Berlin, then moved on to various postdocs where she got this feeling of North America is maybe not a bad place, and ended up at San Antonio, right?
Yep.
As San Antonio for a couple of years before she moved over to Tulane, where she's been for many, many years. And she works on, well, pretty similarity measuring, especially Fréchet distance and similar things, and will tell us more about it.
Well, thank you very much, Teresa. Thank you so much for being here. I mean, yeah, I'm excited to visit. I've never actually visited here before. I don't know why. So, but it's exciting to be here, and thanks for coming to my talk. So, and feel free to ask questions in between if you have questions. So, we can just be all relaxed and easygoing. So I'm going to talk about shape fetching for curves and graphs, and so the way I put it here, I said that I want to talk about geometric distances for curves and graphs, and from shape matching to simplification. So first I'm going to introduce what I mean with shapes. So those are discrete geometric shapes. Then I'm going to talk about distance measures. And then shape matching, and then shape simplification. All right, so shapes. So I want to talk about discrete geometric shapes. So think about a finite set of points. I have n points, right? I could have an infinite set of points, but then I can represent them in a finite way. So I have like n line segments or n triangles, things like that. Right? Or I can have a little more continuous shapes, continuous discrete shapes, weird, okay. Such as curves, for example. Right? So I have curves that consists of n-line segments, and those have applications, they might come from GPS trajectories, which is what I've been working with a lot, or that could be protein chains or so, right? But there are more of these like one-dimensional continuous discrete shapes, such as trees, for example. So this is a plant root morphology over here, and this is a new one that we or straight out geometric graphs. So I have like a molecule over there, or that's a portion of a robot. So yeah, so the things I pointed out are a lot of them are these are one-dimensional embedded shapes, and this is what I want to concentrate on for now. And there's lots that has been done for curves, but not so much for graphs. So when I say graphs, I mean these geometric graphs, and I get to what I mean with that. So yeah, so why graph? So I personally come from this from road networks. Basically, I actually also had some work on constructing road networks from GPS trajectories. Yeah. But overall, it's an interesting question to compare different road networks. You would say, well, isn't there just one ground truth of the road network exists? Why do I need to kind of compare them? Well, if you look at different data sets, they actually look different. There are various reasons for it. One is that the centerline representation, it's sort of where does the centerline go exactly? So the geometry isn't like perfect with different vectors. And here is it's an example from two road networks, and one by red and blue, from two different places. One is OpenStreetMap, and the other is TomTom. Was Canada. And so you see that they're similar, but have like omission, like they're not exactly the same, right? And so that's where my question comes from. Like I'm going to compare what has changed, like embedded, like drawn, right? So okay, so in order to get to how do I define this graph, like first what's a curve? So a curve is I have a map from 0 to R. Like normally we're just gonna stay on two on people, but right. And so similarly, the kind of graph I'm looking at, and we're gonna call it the geometric graph. I think of that as being a graph with vertices and edges, just combinatorially as usual, and then a mapping into, let's say, RD in general. And that mapping should be homomorphic with image. That means then it's an embedded graph without cross. But if it's locally, where there might be some glitches. And normally I will think about the embedded graph setup, but most of the things I'm actually talking about. And so here, example, this is embedded graph, this is a curve graph, and typically, yeah, and so basically what was mapped out is mapped various points and edges to curves, and typically I can take more than vertices because like. I mean, they're good for the geometry, but not like the combinatorial thing there doesn't make a difference if I think of those. Hmm? Oh yeah, so basically so here, that just means that kind of locally, if I just look at locally the embedding, that's always like basically the one point here is just like a one little exception. So if I put just locally little to the left, little to the right, kind of locally, I can find a little epsilon neighborhood where it looks just like nicely embedded. So it really doesn't matter. It basically means like I can handle in many other cases if you control bridges, as long as nothing else nasty happens, like as long as they still intersect nicely, I can handle that, but we can just think about this kind of, like, layer.
But some of the genes embedded on two plates.
No, yeah, oh, yeah. But yeah, let's just think of that. But the way that they kind of like curves, right? Curves have the image and like embedding, right? That's a little bit one to think of this graph as well, because I think of those as being general. One face. All right, so then what is shape matching? So shape matching is well, assuming I have a difference between two of these shapes I'm looking for. Shape matching, well, the question is how similar are they to shape? Well, I make transform one shape to make it closer to the other shape. Maybe I'm going to translate it or translate and rotate it. And try to distance measure and then it'll need a full partial because it only two variation. And so shape, basically, we're given it a shape and the metric or distance measure between those shapes, and also a set of group of transformations, like think translations or rigid motions. And I want to basically minimize over all the transformations my distance measure between the transforms, like set A and B. So I want to kind of transform one shape to bring it as close as possible. Like, translate one shape to be as close. That's shape matching. And simplification is yeah, so with shape matching, I'm giving you two shapes, right? A and B. With simplification, I'm just given one shape. And I want to find a simpler shape that ideally have control distance to my original shape and also kind of lower complexity. That's what I mean. So like just the idea that I want a curve like this, would it be nice to just have a simplified curve? And I love the more detail, but that's what we mean. And here, just there, then your kind of the shortcut will become a tricky question. Like, which shortcut about and what is the shortcut? And yeah, that's all right. So now I first want to talk about distance. So first distances and shape matching, then simplification. That's it. So distances for curves and graphs. Okay, first the Hausdorff distance. So the Hausdorff distance is, well, defined here what's called the directed Hausdorff distance, which really just defines neighbors 2 points. Have you guys seen the Hausdorff distance? So basically, the way to find the directed Hausdorff A to B is for every point in A, you find the nearest neighbor in B. So for every black point in A, for example, I find the nearest. Yeah. So and then I take the maximum of all the distance that I get, and then I get the spread here, right? But this thing is not symmetric because if I take the direction from blue to black, right, then every blue there's the black one. And unfortunately, this is technically far to the left. And so then I get this green distance as the maximum of all of those distances I get from these nearest neighbor assignments. And then the Hausdorff distance is the maximum of both. So it's basically nearest neighbor assignments, and you take maximum distances there. Now, so for point sets in R2, you can come do this in again using neighbor just like lookups, right? And also do this for segments in R2. But the problem is that this is just the nearest neighbor experiment. It doesn't take continuity in any way into it. So if I have these two curves then each blue point is an orange point nearby and vice versa, but it's kind of the nearest the assignment like torn to pieces. So it's not continuous. The assignment is not continuous. And here to graph, like the blue one and then the red one that happens to have two connected components, and it doesn't check connectivity or anything. So it's not really good for continuous shapes. What is good for continuous shape is the Fréchet distance. And so for between two curves, it's defined as follows, where we minimize all reparameterizations and then take the maximum leash length. So this is golf distance visualized with the men together and then hold each other at the leash, and then moving on to move forward or backwards, but here moving as one possible kind of joint sketch of them. And what I'm minimizing overall and the procedure is the minimal possible leash, right? So think of a retractable leash. So very good. Appreciate it. Okay, so how do I compute the Fréchet distance? Because it kind of sounds a little crazy. Right, if you spoke of the interval of a reparameterization. So we compute this in a free space map. So this takes curve F and it rolls it out on the x-axis and term G on the y-axis. And actually the way this is drawn is built old school. So I mean it works, but you can roll them out using their natural parameterization. Using a parameterization, begin this privilege, and it can be their natural parameterization just by arc length. So really the kind of width and the height of the cells, they could also and probably should represent the lengths of the line segments. And then you're cheating a little bit. Give yourself a delta greater than 0, and you want to just decide whether the Fréchet distance is at most delta or not. So given that delta, we can now, so I have this product space essentially of F and G. And so for every point in here, it corresponds to 2 points in the on the original curve. And if the distance is at most delta, I would have point white. And if I have a point here where the distance is greater than delta, I color it. So it turns out that the free space in one cell, which is one line segment times one line segment, is an ellipse. It's really just because it's an affine map of a disk, an absolute. And so now why did we compute this free space? Well, a monotone path in this free space in this free space, so that's just all in the white area over here, corresponds to reparameterizations of our curves. So basically the Fréchet distance is symbols epsilon if and only this path exists. And you can compute that using dynamic programming by, all right, I'll get to dynamic programming in a moment. All right, little demo. Okay, so Peter Schäfer actually made this Fréchet view tool. Okay, now let me play with the zoom a little bit with the screen sharing. You shall see my entire, well, maybe not. Okay, yeah, so here's an example of curves. Think of it starting at the top, down at the bottom. And then now here the free space is now red, which is a little confusing, but it's not white, but it's red, but that's okay. And you can see basically how it changes when you kind of play with epsilon here, right? Oh, I'm sorry, it's delta, right? Yes, right. Epsilon is delta. I know, I'm sorry. Yeah, I know. Yes, but thank you. Good point. Exactly. Yeah. So yeah, so delta is that parameter, exactly, right? And basically you see that at some point there's like a that's connected enough and you have a path in there, right? And at some point the path disappears, right? And actually so what happens here is also you can kind of see how the man and the dog walk. So for this over here, you see the kind of the green segments, like how the man and the dog walk, right? Here they kind of walk together, right? They still walk together. And now here there's this horizontal segment. This horizontal segment, you see there's this like little point. Oh, this point over here. Okay, kind of. What did it do here? Cool. Okay. This point over there, that means the blue man waits while the red dog walks, right? And now they continue walking together, right? So, anyways, it's a nice little tool to play with. To the presentation. So yeah, and so how do we compute this? Using dynamic programming by propagating onto the boundaries of those cells, whether like which points are reachable with a monotone path from the lower left corner. So these are reachable. So you just go like row by row, bottom to top, kind of standard dynamic programming. Right. And once you're at the top right corner, you're like, yay, and trace back. So standard dynamic programming, so it's not surprising. And then in practice, you would then optimize over delta, using some bit precision, maybe. There's also this thing called parametric search you can do to kind of, which is not fun to implement, but has been done. But where you basically add a log factor. So yeah, so that's a Fréchet distance. And there's actually this quadratic barrier. So there's a conditional lower bound that says that it's essentially it cannot be strongly subquadratic, the runtime. And there's just recently last year been a slightly subquadratic so it doesn't have to be n squared, like capital N is just the max of n and m. Yeah, so it doesn't have to be n square log, and it can be n square polynomial. Oh yeah, and there's different variations of the Fréchet distance. One is called weak Fréchet distance, where you still have to find a continuous path in the free space, but it doesn't have to be monotone. It can go up and down, left and right, So meaning the man and dog can backtrack. And I don't even want to go into more detail, so it's similar. It can be done slightly faster, but And then there's this notion called discrete Fréchet distance, where we really just look at the their map. Oh, capital N, yeah. It's the maximum of the complexities of both curves. Oh, N and M. Okay. Just so that I don't always have to write N times N. N times miniature. Yeah. Yeah. There's also the notion of integral Fréchet distance, or most recently catchily named continuous dynamic time warping distance. So where you basically look at the path integral over these the reparameterization there in free space. Yeah, I don't. I don't want to go into. So they have approximating for not L2 distance. Well, L2 distance makes things nasty.
In what sense is it hard to compute?
It is, well, I mean, like the great thing for like L2 is, they have different like this is your even how came up with the station for them.
I'm just curious, what model of power did they use there? Like, you write transcendentals.
It's
Especially.
yeah, exactly. That's the underlying thing, exactly. So yes, because for this you care about the number that's computed, right? All right, but now to graphs. So how do we come up with distances kind of sort of like that for graphs? And so one idea, and we can come up with various kinds of things. I'm just gonna like mention two of them here. So one is the traversal distance. So the idea here, so this is not a symmetric distance. So so what it does is we have two graphs and we're looking at traversals, which are just kind of just continuously walking along and traversing the graph. So turning the graphs into curves. And so I want a partial traversal of a full traversal of G and a partial traversal of H. And that can be done in n square log n-ish. So here's an example. So I have G and H, and now think of these as being on top of each other. Yeah. So so the idea is, and here's a traversal. So the man and the dog will walk together very close by of each other. Like. So that will give us a small traversal distance. So that's the idea of this one. It basically looks at all possible of these traversals and then minimizes over that. And this can be done by looking at kind of like a joint free space diagram of graph times graph and yeah, finding a curve in there.
So traversal, you were allowed to repeat where you were,
Yes, you are allowed to repeat where you were. Yes.
but you have to say that.
Yes, for G.
Project.
For G, exactly. So G has to visit everything, but you're allowed to go back and forth. Exactly. Which sounds counterintuitive, but yeah. But yeah, so that's one way to kind of like hey, and these like recently like vectorize like a graph, right? So basically I'm turning my graph into a one-dimensional object by just looking at these traversals. So this is one way. It's sort of surprising how good that works, you know. Yeah, but something that is a little more takes more of the graph topology in that sense into account. Is what we call the strong and weak graph distances. So the idea is to have these graph mappings, which are continuous mappings from G to H. This is also again a directed distance, and so so they're continuous maps, meaning they send each vertex of the first graph to a point somewhere on the second graph, and then it sends each edge to a single path. Such that the Fréchet distance, and then we look at the Fréchet distance between the edge and the curve. So examples, all of this makes more sense to me. So here's another example of so here the traversal is and think of them. So they walk together. Now that I'm mapping, but here the P points to each other, the blue points to each other, the vertex to vertex. Okay? So if I do that, okay, then eventually I'm going to have that red edge over. And then red edge has to be mapped to a path of the other, which unfortunately is kind of long path. Right? Well, I need to map it somewhere. And that, if I map it from each other, has this so that's the larger graph system. Here's another example that here just with a traversal that can traversal doesn't one graph doesn't happening all kind of the roots again. This edge will cause trouble because of the way how we map it to the edge, which then yeah.
What is the distance?
Yeah, so this is like so because I'm supposed to compute the Fréchet distances between the mapped edges, between the edge and the mapped edge. And this would be the distance ballpark for the grid. Yeah, here both small. So, yeah, so we have that, yeah, this inequality between these distances, yeah, unfortunately, this strong distance that uses the strong regular Fréchet distance is NP hard, but polynomial time for trees to compute, and the weak distance is polynomial time for slightly well-behaved plane graphs. Yeah, so that's one way one could try and define a Fréchet-like distance for graphs. All right, so those were the distances. Now let's come to matching. So matching, this is what we had before, like that was just.
So even in the 2D, I mean, it's like when traversals may have and then you're losing this notion of dimension of the topology. Like I can map a circle to a point.
Yeah.
So, and this distance with all of them will that problem. Is that even a problem? Like I can have a tube here. And things here. And now we're defining what would be the notion of distance between these two objects.
Right, so it's basically, yeah, these distances are allowed to so they're not injective, right? So they might just like collapse several things onto one thing if they're close enough by, and it's yes, that might happen. Why would we want this? Is that a good idea? Good question, right? That is a good question. Like, what is it that we, right? If we want if we want isomorphism, then we have isomorphism, right? So that's another like notion we could try, of course, right? But that seems to be more combinatorial. It seems to make sense that if there's noise or whatever, that if you have some close by kind of structures, that you're allowed to collapse them into one. Yes, but some collapsing like this definitely will happen, or is allowed.
You know, pressure distance, you're thinking sim.
Yeah.
Which is a very worst case feature. So it's like something like wrapping is trying to fix this problem. Like they basically take an integral of the distance.
Right, yeah, exactly. I mean, hey, I'm all for the integral. But only recently we were even able to try to compute or approximate it. Like, yeah, so yeah, exactly. So the integral, whoops, here, the integral for Fréchet distance, absolutely, that's the one that takes an integral over everything, right? But it is very hard to deal with, to compute this, yes. So yeah, actually, we thought until recently, yeah, I mean, well, it is hard to compute for L2 exact. So because you just get kind of messy numbers, incidentals that you have to.
But you've actually even used this thing for trying to other purposes.
Yeah, no, but you're totally right that the outlier is a problem. I mean, absolutely, right? Yes. I'm with you, absolutely, I know.
It's the clustering version of these things you want to get rid of epsilon of shapes. Then
yes, so there are options of like K Fréchet distance where you're allowed to kind of they yeah, absolutely, yes. So there are things. Okay, so okay, so shape matching approaches just quickly so we can sort of exactly like exhaustively search the space of transformations, which we somewhere talk about often via the decision problem check. approach for subspace of transformations, and I'll give you some examples of what I mean. Or of course, there's lots of heuristics, right? There's a different closest point, there is shape signatures that one them, right? So it's the way or just avoid the whole shape matching framework altogether, which is defining different distances, like designing distances that are invariant transformations from the beginning, such as intrinsic distances, that look at intrinsic lengths and just compare the lengths, but then you don't have the shape compared to its extrinsic space that it lives in. Yeah, but I'm going to talk about the first two. Now, okay, this is what's known for Fréchet distance under transformations. And the point is that it's doable at polynomial time, but the polynomials are here, right? So even for translation in 2D, we get n to the 8 log n. Nasty, right? I mean, like, right? And so, yeah, and so this is based on configuration space approach where you want to answer the decision problem for a given for a given delta and construct a set of valid transformation. So let me show you how one gets to those. So this is for Fréchet distance, right? Not for curves. Yeah, Fréchet for curves. So when we have a free space diagram, one of the kind of critical events that can happen is that a white free space opens up on the film. Right. So it just kind of opens up just now when I kind of for this particular So what does that mean in the real world? Right. So when you have this see there, this over here, right? That means that I over here corresponds to a point on the one curve, as you see up there, and this J part, that's the line segment on the other. And this exactly happens when there's this space there. This means that this point I is the distance exactly down to. So that's a critical set. So what translations can I have that will put my point into exactly distance delta to my line segment? Well, I get this whole racetrack of possible translation that will basically put my point all, in all possible, like exactly distance. So this is, so I get a racetrack like this for every line segment and a point pair. I get a racetrack in translation space that gives me these critical concepts. So there's quadratically. Now, unfortunately, that can be given. Because on the right, the setup is what we had in the example of the dental action, where the blue man was waiting and then the dog was walking. This looks like a horizontal kind of thing in the space there. Now, if I change the epsilon and make it a little smaller, then these spikes go so that the left spike goes up, the right spike goes down, and now it's not monotone. So that's a problem. And if you look at closely, this can happen with kind of these 2 points in the real world. They're epsilon the intersect, and that intersection lies in the line. Anyways, I get these 2 line segments in for critical translation, and unfortunately there's NQ. So now I have NQ little shapes that I'm arranging. And I need to compute the arrangement of all of these shapes. So it's NQ shapes in 2-dimensional space of NQ squared. That's the first, n to the first. It's n to the 3 times 2. So those are all the different, potentially combinatorially different translations I have to try out. And then one brute force, this is here, one brute force for each of those translations then computes the n squared for distance. That's why it's n to the 8 log. Yeah. So recently, so this is for the arrangement. the 3K and the 3X. Yeah, the class 2 was intended for computing the shaders and from scratch everything.
They hope that the second one, they don't,
And it can be, yes, exactly. So recently, completed out last year showed that it can be done by updating these using offline dynamic grid readability to make this faster so that it's not in square than what it words. And this is actually by originally by Brinkman, and all they did was for discrete. So, but it's still not great. And also there is a lower, there's an additional lower barrel that it takes into the for discrete crochet. But there's still like a gap between into the 4 and into the 7 point.
so is there a new one that says it depends on chase necessary?
No, exactly. There's no, why not? By point being exactly, there's all these like crazy high polynomial. And the only lower bound we have is the so we have a this n to the 4 lower bound for the discrete crochet, and we also have an n square lower bound for continuous crochet. And that's it. So yeah, there's definitely a point. But then another thing, of course, one can do is approximate matching. Why do we do approximate? It's like two things approximate, right? So let's, for example, if we just have like two shapes like this, I mean, let's just put a bounding box around them and put whatever the center of each other on top of each other, find the translation. And here I'm going to really use the upper left corner. But compute that and use that as a translation, that should be good enough, right? I mean that will be. It's not even cool that it's not that bad. This is actually pretty good. So because let's see, if you look at the best translation for blue here, which is the lighter blue one, then when you look where the kind of 2 points that define the bounding box for the yellow, where do something that's a little delta. So therefore, the x and y portion, they're delta. So therefore, this is all, we just move the upper left corner of delta in x and y. So meaning overall in the square root of 2 times delta. So overall, this gives you 1 plus square root 2 approximation. So 2.4 for 2D translations, which isn't bad. So this thing is called a reference, actually. And there's other reference points. There's a thing called the Steiner point, which is a very specific point. Any other additional point. This one is essentially like if a standpoint with the edges of the country model. And kind of if you did this by looking at all possible lines, so that gives you a 2.7 approximation. But not bad, and the runtime is okay, so that's good. And this is, it all comes from these reference points, and them having this nice Lipschitz property, and then the Lipschitz constant factors in here, approximation factors. So that's good, right? Now another idea is to do some pinning. You can kind of exploit the discrete meshes. So for especially for curves, shaders and for curves, what you can do is, well, there's a start point to mesh. Have to be matched to each other in the Fréchet matching. So just translate them onto each other. Go on in the morning. And that gives you 2 approximations. Yeah. So
this one, Okay.
No, it's well. Let's say we're just doing translation. If you're only doing translations. So if, yes. Yeah, if we're only doing translations only, right, not rotations, then I just translate them onto each other. But yes, the whole point is that we also want to rotate, we'll optimize over all rotations.
So in any of these things you said in 2 dimension they're constant, but k dimension is simple and
In higher dimension, that would,
not sure what I should like this like that. For the other,
yeah, no, I mean, what actually, it's just like the top left corner is just like the top left corner, so yeah, it's good.
yes, the same way for those, like the Fréchet or Carola.
Yeah. Because that's just by triangle inequality, and that is still a factor too, you know. It's just by triangle inequality that I just kind of move, so I know the 2 points have to be mapped to each other. So it's just plus another instance of delta, yeah. Yeah. And then one can also kind of do some refinement and grid sampling and so on to get things down to one from epsilon approximation, but you know, if you're already close, you can make it closer by just putting in epsilon. But so what do we know for approximate matching for curves or Fréchet? Well, like I said, this triple approximation with just like putting the start points onto each other, right? So that gives me a 2 approximation of order 1 times 4 translation. And we can do the grid sampling in addition around, and that gives us then a 1 plus epsilon approximation. But what about reference points? Well, the reference points for Hausdorff distance, which is the one I talked about there, are also reference points for Fréchet distance, trivially. However, the resulting approximation for these reference points, it really just fixes the translation, but not any rotation or scaling or whatever we might do, right? So, and in fact, the reference point algorithms for like the Hausdorff distance will then just proceed to, well, okay, we fixed the translation and we still need to optimize over the rest. So optimizing over the rest for Fréchet for rigid motions would mean that we would to like use one of those expensive algorithms that I just showed for rigid motion. So then we get to n to the 4.33 even with the latest. Good. So that was great. So yeah, would we have anything better? And then lower bounds. So lower bound, yeah, so the only lower bound we have for Fréchet under translation is n squared. Actual lower bound, 4, sorry. That is a lower bound for the complexity of the configuration space. That's actually not even, who knows if one actually has to do this just tells you like an example where n squared complexity. And then there is and there's very strong like that Hausdorff distance for non-Fréchet. And like I said, there's an additional lower bound for pre-Fréchet for spring stage. And of course, graph is potentially so I think the configuration space approaches for the Fréchet metric will they carry over to the Fréchet like distances I introduced, but I'm not sure. Yeah, so I'm gonna think and the standard reference point approaches definitely will not work because the distances I mentioned there are not symmetric. They really only match potentially or function. So that's why I choose mobile reference. I think since we have like questions already, I could continue. Sure. So simplification. That was the other topic. to talk about, right? So where, again, this was what we were thinking about. And so for curves, so again, now the setup is I have a single shape, let's say single curve, and that's the Y. So the standard is this Raymer diamond square, which is given my curve, and I am given it. And so I look at the first possible shortcut from the start with the endpoint, and I look at the furthest away point. That's that. So if it's greater than that, then I'm just going to subdivide and subdivide, and then continue that. So I subdivide perfectly. Like a shortcut now, that seems to behave, so I'm keeping that, you know. And then look at this one, and that marks just and that is great. I'm gonna fucking be. So that is the standard big one. Now, so there's a few variants for like simplification, like the way I do this, because I know I want both the complexity of B as well as the distances to be small. Well, that's kind of like too many things that want to be small at the same time. So yeah, so we can think about different ways to deal with this. Often people just fix one and then kind of optimize the other. So often we're going to look at the min k, which will fix the delta and a curve of some complexity, the distance delta. And then there's this notion of shortcut graph. And I didn't draw all the shortcuts here, but I think that already brings the point across. So I can look at all pairwise and shortcuts and then check if they fulfill this at most delta here. So then I get a subset of shortcuts and I just kind of do kind of so that can be done in square-ish.
So what?
Yeah. So basically, right, so I'm going to check if a short has an invalid in the sense that the curve in between it and the short that all points assisted among delta to my short. Right, so I can check this for all lines. And if I do this efficiently, you know what, I have n square of these shortcuts. And then I have this valid shortcut that I keep. Right? And then and technically that is a direct, right? Because the shortcuts really go from one to the other. And then I just want to find in this graph of possible shortcuts, like a shortcut. Which, you know, now you have the graphic and square. Yeah, exactly. Yeah, and then there's this notion of local versus global simplification. So really, what we did here was local simplification. I just talked about the distance of the piece of the curve compared to the shortcut. Right? What we like local is global. But what we wanted, this was actually global. I basically said I want the global distance between the shape to be like none of these approaches to do it. And there's also the notion of mid-lead. So there's like if so we have the delta neighborhood. If like this would be a mid-lead that just stays inside the neighborhood. So here I create. So yeah, so if you think about it, this one was vertex perspective. I have to use vertices of the input here too, and here too, actually. But the new thing is who doesn't need to do it? Maybe we don't want to use right? So it's all these different variations, right? And so here's an example where the second one here, second row, so shows you that this is the global simplification, the red path of the global simplification, that's exactly input curve. But it's not local because the first shortcut the curve already goes outside that neighborhood there. Right? So it's definitely not low, like distance wise, it's kind of further. So so it's just the global versus local criteria. And here are a couple of examples. So if this is my input curve, and here's my delta neighborhood, then if I'm vertex restricted, if I have to stay on the vertices, then this could be an simplification. That I can do something called curve restricted. I have to come up with vertices that at least lie on the curve. So then it would look like this. And here, if it's non-restricted, just have to lie. And in fact, so what can you do? So this is a curve. There's all these different options now for this. So you see that if we use the house surface, then all of it ends up being in the hard then. For the Fréchet distance, so this is simplification in this global setup. For the Fréchet distance, we actually have a cubic algorithm as well as the cubic conditional loop. So that's good, you know. Yeah. So this is what's known. What we do for the cubic part here for the Fréchet distance, which is the vertex restricted. What we do is we build this free space and we take a shortcut graph. So if this was my input, but if this is my input graph, and I compute all the shortcuts which are there, and I now like use that to compute myself and define a free space diagram. And this shortcut graph times the input curve, right? So then I get this context space, which has all these different panels, you know, and I can compute like a free space diagram. So that's a kind of visualize, right? You maybe have to take a shortcut graph, use the curve, you know, and then you want to find a path in there. It's a minimum link path. But you can't compute that. Yeah. The bookkeeping can be done in compute. But that's where that comes from. So the shortcut graph idea kind of translates to it. And yeah, so for graph simplification, so this occurs. For graph simplification, there's very okay. So there's some hardness. So the first one here is that one is vertex restricted, local simplification, and you're only allowed to remove degree 2 vertices. And that is already hard to approximate. The second one here, that's a totally different setup. That one is you want to do a homeomorphic simplification. So you have your graph and it lives inside some polygon, which could be your epsilon. And trying to find a simplified graph that is homeomorphic to the original one is NPL. That's not good. If we look at the graph distance, like the strong graph distance, we have a few results for these different restrictions. So let me just show you the pictures over here. So here was the input graph. So one restriction that's like a subset of, well, we're looking at vertex restriction only. And one is if the resulting graph needs to be a subgraph of the, then we would, in this example, get the red. And the little green arrows are what we get from the graph mapping, because the mapping has vertices and groups. So if we don't care about subgraphs and only one vertex restricted, we would get the blue. And leaf restricted, we came up with something which is sort of similar to the Fréchet curve, so we have to map the star points onto each other. So we have to map certain leaves onto each other. Like they have to map to each other. Then if all these 4 leaves have to be mapped to each other, we'll get this graph, which is not much simplified, but I got rid of them. And so we have a few results here. Many of them are hard. weekly entry that's valued, and that is called the graph distance, and there's a few things for the traversal distance. Yeah. So. Yeah, and that brings me to my summary. So, great, so we talked about a lot of things. Thanks for sticking around. So yeah, first for distances, geometric graphs, then matching other transformations, and exact and approximate, and then simplification, right? And sort of some of the open problems around this are, well, any exact or approximate algorithms for graph matching, any reference, like we have nothing. Or tighter load, for matching, or even for curve matching under translation. Right. The best we have is n squared for the configuration space or n to the 4 for discrete Fréchet. Kind of very limited the look. And then really faster matching. What about special curve? Like we have this notion of curves, which I honestly think restrict the free space, the complexity of the free space, well, in a way. And I wonder if that could help translations to also help restrict the complexity of the translation space. Maybe. Yeah, and for graph simplification, well, there's lots of open cases. So for example, vertex restricted for very simplest thing. We don't really know. We have this p-test algorithm, which is just fun, but yeah, we would like to know where it actually stands in complexity and yeah, what scenarios able anything where it can come quality guarantee, but that's not just. Thank you. Okay.
We did have a lot of questions to run the class. So why did you think we have?
Questions like. One other question, the last one. Decoding graph, what happens if you like it out over this? Then will be fine for the.
I mean, you can define it for sure, right? Yeah. Good question.
I think that's the first natural definition. Like you're saving more either micromatic perfect.
Right, exactly. Yes. So yes, I like the Earth first one. The question is, I don't know what's known for translations. I'm trying to think, like, I'm not sure what's known for, yeah, what is known for Earth mover systems under translations in general. I feel like it's something. I'll have to look that up. Yeah. Absolutely. I mean, Earth movers, and yes, so maybe that's something for sure to look into because that's definitely a natural distance.
Yeah. Or you know it's
I don't think so for grass, but yeah. Cool. Well, thank you.
Thank you. Carola is around for the rest of the day, so